So still dealing with chapter 6 and the standard deviation, I want to talk about what's called the normal model. Now, the normal model is, you may have heard of this as called the bell-shaped curve. So it's probably the most popular. We'll use quite a bit of we'll be dealing with normal models in quite a bit of our course, especially in the last half. But the normal model has some characteristics, and one of them, by the way, this is not perfect. When I draw the normal model, I draw my line first across here, and then I'm drawing kind of a bell-shaped curve, and they're not perfect. So right in the center, a normal model is symmetric, and right in the center is our mean. Now I'm going to treat this as a population, so I'm going to have my mean, which remember mu from the last video, mu is the population mean. And sigma is the population standard deviation. So there's a characteristic on the normal model, and that is that if you go out 3 standard deviations either direction, you pretty much cover the whole normal model. So from my mean, I'm gonna mark off 3 tick marks here and try and expand it all the way to kind of the end of my drawing. Again, it's not perfect. So each one of these marks is going to be a standard deviation. So I'm going to label this one as mu plus sigma because it's a standard deviation above my mean. This one would be mu plus 2 sigma because it's 2 standard deviations above. Mu plus 3 sigma, that's 3 standard deviations above. This one is going to be mu minus sigma, mu minus 2 sigma, and mu minus 3 sigma. So when you go out 3 standard deviations, it covers most of it. Now, when you just go out 1 standard deviation either direction, you're going to capture about 68% of the data is going to be captured within 1 standard deviation. If you go out 2 standard deviations, you're going to get about 95% of the data captured within 2 standard deviations. And if you go 3 standard deviations, you're going to get about 99.7% of the data, which again is almost all of it. So we can pretty much expect, if you have a normal model, you can expect to capture all of your data, almost all of it, within 3 standard deviations of the mean. Now, this has a name, this characteristic, very conveniently named the 68, 95, 99.7 rule, which is great if you remember it with that name, because then you also remember the numbers. It has another name you might hear called the empirical rule. I just want you to be aware of that in case you see it written that way. It is the same thing. I kind of like referring to it as the 68, 95, 99.7 rule because then you're going to remember what those associated percents are. So this is important to remember. I'm going to come back and talk about the standard normal in just a minute because we have a curve for the standard normal as well, and we'll look at that. But let's do an example. So on this example, we've got Environmental Protection Agency fuel economy estimates for automobile models tested recently predicted a mean of 24.8 miles per gallon and a standard deviation of 6.2 miles per gallon for highway driving. Assume that a normal model can be applied. So I want to tell you how we identify normal models with the notation. We use an N for normal, and then the parameters are the mean and the standard deviation. So you'll see this notation throughout the course. So for my particular example here, we've got a normal model, and the mean is 24.8 miles per gallon, and the standard deviation is 6.2 miles per gallon. So this is how I would identify the particular normal model I'm talking about. Be aware, every time you change the mean and standard deviation, you will change the normal model. I mean, it's still going to kind of have the same picture. So we'll draw this line. We'll draw our normal model as best as we can. That is not very good. Let me try again. Okay, still not very good, but okay, good enough. So I'm going to mark this. The mean goes in the center. So this is 24.8. And I'm going to go 3 standard deviations each way. By the way, I'm doing part A because it says to draw the model. So then I'm going to add the standard deviation. So 24.8 plus 6.2 is 31. And if I add 6.2 again, I get 37.2. And if I add 6.2 again, I get 43.4. Then I'm going to subtract 6.2 going the other direction. So there's my numbers. Then they asked me to clearly label it, showing what the 68, 95, 99.7 rule predicts. So I'm going to go ahead and say I'm going to have 68% of the cars are going to have a fuel economy between 18.6 and 31 miles per gallon. I can say 95% of the cars are going to have a fuel economy between 12.4 miles per gallon and 37.2 miles per gallon. I mean, that's quite a spread, notice. And then I know going 3 standard deviations, I'm going to have 99.7% is going to have a fuel economy between 6.2 miles per gallon and 43.4 miles per gallon. So that would be part A. Part B, in what interval would you expect the central 68% of autos to be found? Well, we've already identified that. So it would be the interval between 18.6 and 31 miles per gallon. Part C, about what percent of autos should get more than 31? So let's see where that more than 31 is. More than 31 is this region here. Now you're going to have to do a little math, because if 68%, notice that it's like the side, it kind of bumps up to my line for the 68%. So remember, 68% is between these two values. Well, that means if you have 68% here, and so this is 0.68 or 68%, then think about how much would have to be on each side. It's symmetrical. So 100 minus 68 is 32, so that you have to split the difference between the two sides. So I'm going to have 16% on this side and 16% on this side. So when they ask you about just this part here, that would be greater than 31, then we would expect about 16%. Now I'm going to introduce a notation, and I'm going to say the percent or the proportion of autos, and I'm going to use an X for my data, that would be greater than 31 would be 16. You can say 0.16 or you can say 16%. I guess they said about what percent. This is a notation we're going to use later, so you may as well get used to it now when you see me use it. So part D, about what percent of cars should get between 31 and 37? Now we're not going to be able to do this exactly. 37 is close to 37.2, but not exactly. So I'm kind of looking for this portion right here. So I know that this whole side that we just calculated is 16. And we know that from 12.4 to 37.2, we know that's 95. So take 100 minus 95, and these little tails here, you get 5%, you got to split in half. So we have 2.5% on this side, and we have 2.5% on this side. So if I want to know about, and I want to know the proportion of cars that are between 31 and 37, I want to know about that. I'm going to take 16, which was this whole piece here, 16% minus this tail, which was 2.5%, and I get about 13.5%. Or if you want, you can leave it as a proportion and say 0.135. So that's about what it would be. So you're just kind of using these numbers and using the symmetry of the picture, thinking about what region you're looking for and what math calculation you could do to figure it out. Part E, describe the gas mileage of the worst 2.5%. Well, the worst 2.5% is down here in this tail. So we would be looking at anything that was below 12.4%. So below, I'm sorry, not 12.4%, below 12.4 miles per gallon. So if your car gets less than 12.4 miles per gallon, then you are in the worst 2.5% of all cars. So on this next example, and I know we didn't do exercise 9, but this is talking about weights of yearling Angus steers. And notice they tell you that it's a normal model with a mean of 1,152 pounds and a standard deviation of 84 pounds. And then they ask you, what would you consider to be unusually low for such an animal? Well, they tell you it's a normal model. So I'm going to draw my normal model. You're going to be drawing lots of these. That's a horrible one, but not redoing it. I'm going to mark my mean as 1,152. And because I'm only looking for low, I'm just going to mark 3 standard deviations to the left. If I take 1,152 and I subtract the mean, I get 1,068. I'm going to subtract the mean again. I get 984. And I'm going to subtract that one more time, and I get 900, since I was only looking at unusually low. So now we have to decide, what do you consider unusually low? I'm not going to put the numbers here, but let me mark those. Because we know that 95% is in between, approximately 95%, I should say. And we know that within 3 standard deviations, we have approximately 99.7%. So it kind of depends on what you want to consider low. I'm going to consider anything more than 2 standard deviations below the mean as low. So if I were to look at just this part down here, and it would continue on even below 900, even though we know there wouldn't be very many steer that would be down in that region. So I'm going to consider anything below 984 pounds could be considered unusual, since it is 2 standard deviations below the mean. Now remember, how much is here? 95%, 100 minus 95 is 5. Split the difference. Only 2.5% of the steer are going to fall in that region. So that makes it unusual. Some of you might say, I'm going to go with less than 900, because I think that's going to be very unusual to have a steer that's less than 900. And that's because that would be more than 3 standard deviations below the mean. So it's kind of open to interpretation. 1 standard deviation below the mean would not be considered unusual. 2 standard deviations below the mean or above the mean, if it was higher, that's where you can start talking about it being unusual. So one more thing I want to mention is a standard normal model. Remember when that was convenient to do the standard normal model, every time you change the mean and standard deviation, you have a different normal model. So this, like the ACT and the SAT, this doing a standard normal, this is z-scores, and this allows us to compare 2 models with the same, standard deviation, or the same mean and standard deviation when you change them to z-scores. And the standard normal model converts the mean to 0 and converts the standard deviations to 1. So you end up with a picture like this. So we have a normal model with a mean of 0 and a standard deviation of 1. So how do you convert it? You take your data values, subtract the mean, and divide by the standard deviation for the model given. Like I could do that for the steer model, and I could turn them all into z-scores if I actually had a data set for that. And then I can turn those into z-scores, and then this would be a standard normal model. So we're going to do more of that next time.